Nearly a century ago, a young lab assistant in Arizona spent night after night comparing photographic plates of the sky, hunting for a single speck of light that moved against the fixed stars. That painstaking search paid off in early 1930 when he spotted the tiny world we now call Pluto. For most of the 20th century, Pluto held the title of ninth planet, even though nobody had a clear picture of what it actually looked like. Telescopes of the era could only resolve it as a faint smudge, so its size, makeup, and even the existence of an atmosphere stayed open questions for generations. Some early size estimates were wildly inflated, based on gravitational effects on Neptune and Uranus that later turned out to be measurement errors rather than real evidence of a massive Pluto. In 2006, the International Astronomical Union voted to reclassify Pluto as a dwarf planet, making it the only world in history to be discovered, celebrated, and then formally stripped of the category that made it famous. For a while, that felt like the end of the story. A small, distant world easy to write off as unimportant. In July 2015, after a 9.5-year journey across billions of miles, NASA's New Horizons spacecraft screamed past Pluto at more than 30,000 miles per hour. There was no orbit and no second chance. Just a brief window to gather as much data as possible before continuing into the Kuiper Belt forever. What came back reshaped everything scientists thought they understood about this so-called leftover chunk of ice. The images revealed a massive, pale, heart-shaped plain that looked strikingly young compared to the ancient, cratered terrain around it. Mountains built from water ice, frozen so hard it behaved more like rock than the ice we know on Earth, rose more than 10,000 feet into a thin, hazy sky. Fields of nitrogen ice appeared to be slowly churning, hinting at heat and motion beneath a crust once assumed to be completely inactive. Layer upon layer of blue haze stretched hundreds of miles above the surface, visible even when lit from behind by the distant sun. But a flyby only gives you one look. Whatever New Horizons missed on that single pass would stay a mystery, because there was no plan to send anything back. What researchers needed next wasn't a better photo. It was a way to read Pluto's chemistry directly from Earth without launching another spacecraft. That's where the James Webb Space Telescope entered the picture. Unlike New Horizons, Webb doesn't fly past its targets and snap pictures. It reads light itself, splitting it into individual wavelengths to reveal the chemical fingerprint of whatever it's observing. Pointed at a faint pinprick of reflected sunlight billions of miles away, Webb can determine which molecules are present, how warm different atmospheric layers are, and how conditions change over time, all without going anywhere. Starting in 2022, once its instruments were fully calibrated, Webb finally turned its full attention toward Pluto, and what came back over the following years amounted to something closer to a full diagnosis than a simple update. Pointing Webb at Pluto sounds simple, but the engineering challenge behind it was significant. Pluto and its large moon Charon sit so close together in Webb's field of view that separating their individual heat signatures had previously been almost impossible. Earlier generations of telescopes repeatedly tried and failed to detect certain faint signals from Pluto, not because those signals didn't exist, but because the instruments couldn't distinguish how much heat was coming from Pluto itself versus bleeding in from Charon nearby. Webb's much larger mirror and far more sensitive infrared instruments finally solved that problem, letting scientists cleanly isolate Pluto's own thermal signature for the first time. That capability set up one of the most surprising confirmations in recent planetary science. Back in 2017, a planetary scientist at the University of California, Santa Cruz, proposed an idea that struck many colleagues as backwards. On Saturn's moon, Titan, atmospheric haze traps heat and warms the surface below. This researcher argued Pluto's haze might do the opposite, absorbing sunlight during the day and then radiating that energy back into space as infrared heat faster than Pluto's extremely thin atmosphere could hold on to it. In other words, the haze wouldn't act like a blanket. It would act like a radiator, actively bleeding heat away from a world that had almost none to spare. At the time, there was no way to test that idea. Once Webb's mid-infrared instrument became sensitive enough to separate Pluto's faint thermal signal from Charon's, a research team based at the Paris Observatory used it to measure Pluto's atmosphere directly. Their results, published in a major astronomy journal in mid-2025, confirmed almost exactly what had been predicted 8 years earlier. Pluto's upper atmosphere really is being actively cooled by the haze particles suspended within it, and the effect makes the atmosphere roughly 30 degrees Fahrenheit colder than earlier models had predicted. Researchers now describe this as a genuinely new kind of planetary climate, one unlike anything else observed in the solar system. Pluto isn't simply cold because it's far from the sun. In a real sense, it appears to be actively refrigerating its own atmosphere. Scientists are still working out how far the implications reach, including whether similar haze layers might be shaping conditions on other distant, hazy worlds like Neptune's moon, Triton, or even hinting at what Earth's atmosphere may have resembled billions of years ago, long before oxygen accumulated in our skies. There's a second, quieter discovery tied to that same haze. Even the extremely faint sunlight that reaches Pluto is enough to break apart methane molecules high in its atmosphere. Those fragments don't simply disappear. They recombine into heavier compounds, eventually forming reddish-brown particles called tholins that drift down and settle on the surface. New Horizons caught early hints of this process back in 2015, and Webb's more recent observations have helped refine exactly how it unfolds, adding another layer to a world that keeps turning out to be far more chemically active than its frozen, distant reputation would suggest. The detail that tends to stop people in their tracks is what tholins actually are. They belong to the same broad family of organic molecules some scientists believe may have once rained down onto early Earth, potentially supplying raw material for the chemistry that eventually led to life. On Pluto, that same basic process has apparently been running for roughly 4 billion years. A slow, continuous snowfall of biological building blocks landing on a surface too frozen for any of it to ever spark into something alive. To grasp just how extreme that cold really is, the numbers help. Sunlight reaching Pluto is roughly 1,000 times fainter than sunlight reaching Earth, meaning even high noon there would resemble a heavy twilight here. Surface temperatures typically sit between about -387 and -369 degrees Fahrenheit, more than 250 degrees colder than the coldest temperature ever recorded anywhere on Earth. At that range, nitrogen, the same gas that makes up most of the air we breathe, freezes completely solid and becomes part of the landscape. Scientists care about this ongoing chemistry for reasons beyond its strangeness. Researchers studying the origins of life on Earth have long debated whether the first organic building blocks formed here on the planet itself or arrived from space, carried by comets, asteroids, or slow chemical processes happening in icy environments, much like the one now observed on Pluto. Studying a real, ongoing example of that chemistry running continuously for billions of years gives scientists something they could never get from Earth alone. An active natural laboratory for a process that, on our own planet, finished playing out and left behind only indirect evidence billions of years ago. In that sense, Pluto isn't just a curiosity. It may be one of the closest things researchers have to a working model of the raw chemical conditions that existed before life ever began anywhere. That leads into the third major finding, and it's the one that tends to unsettle people most once it's explained properly. Pluto has been slowly leaking into space for billions of years. Methane and other light molecules drift upward through its thin atmosphere, slip past its weak gravity, and escape outward. Scientists already suspected this was happening, but for a long time nobody knew exactly where all that escaping material actually went. It wasn't simply vanishing into empty space. Something was catching it. That something turns out to be Pluto's largest companion, a battered ice moon roughly 750 miles across that orbits in an extremely tight gravitational partnership with Pluto. Most of that moon's surface is fairly ordinary water ice, ancient and heavily cratered, except at its poles, which are stained a deep, unmistakable reddish-brown, unlike anything else visible on its surface. For years, researchers suspected a connection between that coloring and material escaping from Pluto, but they lacked the tools to confirm it directly, setting up the next chapter of the story. The mechanism behind that reddish coloring is tied closely to the moon's extremely slow, extremely long seasons. Because of how it's tilted as it orbits alongside Pluto, its northern polar region spends multiple decades in complete darkness at a stretch, with no sunlight reaching it at all. That makes the pole an unusually effective cold trap, a place where methane molecules escaping from Pluto drift in and freeze solid simply because there's no warmth to keep them as gas, accumulating there for years before sunlight finally returns. Once sunlight does return, it doesn't simply melt that frozen methane away. Instead, ultraviolet radiation and cosmic rays break the frozen molecules apart and reassemble the fragments into heavier, more complex reddish compounds, essentially locking in the dark coloring rather than letting it evaporate back into space. A widely cited study from 2016 showed that methane escaping Pluto's atmosphere drifts across roughly 12,000 miles of space, gets captured by the neighboring moon's gravity, freezes onto its cold polar surface, and is then broken apart by sunlight and radiation into the same kind of heavy organic compounds that color Pluto's own surface. In effect, two worlds locked together in a slow, ongoing exchange of atmosphere and color that appears to have been running quietly since long before either had a name. That moon had one more surprise waiting. In October 2024, a research team based at the Southwest Research Institute used Webb data to confirm the presence of both carbon dioxide, the same gas we exhale with every breath, and hydrogen peroxide, the same compound sometimes used to disinfect a wound, frozen directly onto the moon's surface. According to the published findings, the carbon dioxide most likely came from underground material exposed by impact craters, while the hydrogen peroxide appears to have formed through years of radiation, striking the moon's water ice and rearranging it into something new. Researchers noted this specific combination of frozen chemicals had never been confirmed there before, adding yet another layer of complexity to a moon that keeps turning out to be far more chemically interesting than its plain, icy appearance would suggest. Now picture, for a moment, what it would actually feel like to stand on Pluto's surface. The sun would still be visible, but only as an intensely bright point of light, smaller than a pinhead held at arm's length, giving off no real warmth or glare. You could look directly at it without discomfort. The sky would sit in a permanent grayish-blue gloom, thick with haze, never fully day and never fully night. At nearly 400 degrees below zero, water ice stops behaving like the ice we know and instead acts closer to solid rock, hard enough to ring, almost like metal if struck. The atmosphere, roughly 100,000 times thinner than Earth's, would offer nothing to breathe, though the extreme cold would freeze exposed skin almost instantly, long before that thin air became the immediate danger. Overhead, fixed permanently in the same spot in the sky, the neighboring moon would hang motionless, the two worlds locked so tightly by gravity that each always shows exactly the same face to the other. Pluto's surface holds its own separate mysteries. In one region, New Horizons photographed something no spacecraft had ever documented anywhere else in the solar system. Tall rows of jagged ice blades, some reaching more than 1,500 feet high, made of frozen methane and arranged in long, parallel ridges. Much smaller versions of these formations exist on Earth in certain high-altitude deserts, where they rarely grow taller than an average person. Scientists believe the Earth-based versions form through uneven melting and sublimation across an icy surface, gradually carving taller sections while lower areas erode faster. On Pluto, that same basic process appears to have played out on a far larger scale, over a much longer stretch of time, using frozen methane instead of frozen water. A 2025 analysis of the original New Horizons data suggests these towering ice formations may wrap around as much as 60% of Pluto's equator, forming an entire ring of jagged frozen terrain circling the dwarf planet. Elsewhere, a massive dark region, roughly the size of Alaska, stretches across the equator, colored a deep reddish black, where falling organic tholin particles have apparently piled up thickest over billions of years on some of the oldest, most exposed terrain on the planet. South of Pluto's famous pale, heart-shaped plain, two enormous isolated peaks rise from the surrounding landscape that researchers still can't fully explain. One stands roughly 13,000 feet tall. The other may reach close to 20,000 feet, with a base wide enough to rival some of Earth's largest volcanoes. Both have deep depressions at their summits, ringed by fractures with lumpy, uneven flanks that closely resemble cooled lava flows. Except there's no molten rock on Pluto. If these features are what they appear to be, they're cryovolcanoes. Structures that once erupted, not with melted stone, but with a thick slurry of water, ammonia, and methane forced upward from somewhere deep beneath the icy crust. Researchers remain divided on exactly how these formations came to exist, whether from a handful of massive eruptions or many smaller events spread across a longer stretch of time. Either way, both interpretations point toward the same striking conclusion. Something in Pluto's relatively recent geological history was warm enough beneath that frozen shell to force liquid material all the way to the surface. That internal warmth feeds directly into one of the most debated ideas surrounding Pluto today: the possibility of a hidden ocean buried roughly 100 miles beneath the surface, kept liquid by the slow radioactive decay of elements inside Pluto's rocky core. The evidence isn't a photograph, it's a pattern. Cracks and ridges across the surface line up in ways consistent with a subsurface layer of liquid water shifting slowly beneath the crust, and that famous heart-shaped plane sits directly above what appears to be a positive gravity anomaly, a spot where something denser than the surrounding ice may be concentrated underneath. Scientists find this scenario compelling because similar hidden oceans are already strongly suspected beneath the icy surfaces of Jupiter's moon, Europa, and Saturn's moon, Enceladus, both of which show more obvious surface evidence, including water vapor geysers erupting directly into space in Enceladus's case. If a body as small and cold as Pluto turns out to be hiding something similar, It would suggest buried oceans might be a far more common feature of icy worlds throughout the outer solar system than previously assumed, rather than a rare exception limited to a handful of larger moons closer to the Sun. If that ocean genuinely exists, it has likely been there for billions of years, sealed away completely from sunlight and radiation, fed only occasionally by hydrocarbons seeping downward through cracks in the ice above, sitting under enormous pressure in total isolation. It would represent one of the strangest possible settings in the solar system for the basic conditions life requires, existing with no direct connection to a star at all. Right now, though, there's no way to confirm any of this directly. No mission is currently funded to send a probe back to Pluto, no lander or orbiter is on the books, largely because the journey alone would take the better part of a decade, and outer solar system exploration has rarely been treated as a funding priority. That isn't simply a matter of scientific interest. Missions to the outer solar system are extraordinarily expensive and slow, often requiring a decade or more of travel before a spacecraft even reaches its target, followed by a single brief window to gather data. Much like what New Horizons experienced. Space agencies have to weigh that kind of investment against competing priorities, including missions closer to home that can return results within a few years rather than a few decades. That trade-off means distant, icy worlds like Pluto often lose out in funding decisions, not because scientists have stopped finding them interesting, but because the cost and timeline make them a harder sell next to faster, closer missions. For now, the James Webb Space Telescope remains the only working tool available, checking back in every few months whenever Pluto swings into its field of view and adding another data point each time, almost always making the overall picture stranger than it was before. Here's the detail that tends to stick with people longest. Pluto isn't unique simply because of where it sits. It's part of the Kuiper Belt, a vast ring of icy debris beyond Neptune's orbit, home to hundreds of thousands of objects wider than 60 miles, along with an estimated trillion or more comets. A handful of other bodies out there, including Eris and Makemake, come reasonably close to Pluto's size. Beyond the Kuiper Belt entirely lies the theorized Oort cloud, thought to hold another trillion or so icy bodies stretching outward roughly a quarter of the way toward the nearest star. To put that scale in perspective, the Kuiper Belt alone is estimated to span an area of space hundreds of times larger than the more familiar asteroid belt between Mars and Jupiter. And unlike that inner asteroid belt, which has been mapped in fairly close detail thanks to its proximity to Earth, the Kuiper Belt remains almost entirely unexplored. Only New Horizons has ever ventured deep enough into that region to closely photograph any of its larger residents, and even that mission only managed close flybys of two objects: Pluto and a much smaller, more distant body nicknamed Arrokoth, out of the hundreds of thousands of similarly sized worlds believed to exist out there. If Pluto is genuinely cooling its own sky, slowly bleeding its atmosphere onto a companion moon, and possibly hiding a liquid ocean beneath a shell of solid ice, there's no obvious reason to assume it's the only object out there doing anything like this. It's simply the one close enough and bright enough for current instruments, especially Webb, to study in real detail. Nearly everything else scattered across that same vast region of space remains almost entirely unobserved. So what does all of this add up to? Pluto was never really the dead end of the solar system that a single 2006 vote made it seem like. It turned out to be the beginning of a whole set of new questions scientists are still learning how to properly ask. Out past Neptune, in the cold and the dark, there are trillions of other worlds we've barely glanced at, let alone studied closely. And if one small, formerly dismissed dwarf planet was hiding this much complexity beneath its surface, it's genuinely worth wondering what all those other distant worlds might be hiding too. The James Webb Space Telescope is still pointing back at Pluto every few months, and there's a real chance the next round of data adds another genuinely strange piece to this puzzle.